for the introduction, and I would like to thank the organizer, Thibaut and Karim, for inviting me to give this talk, and welcome to all of you. So I am a chemist. I will give you the chemist point of view on this biomineralization, and I hope that my talk will be understood by all all the audience. So here is the content of my talk. So I will make an introduction. Then I will talk a little bit on bone mineralization, on the composition and the structure of bone mineral. I will focus on bone mineral then, and especially on biological apatites. And I will show you how we can compare the properties of biological and synthetic apatites. Then I will talk about the model of the crystals of apatites that we propose. And I will finish my talk especially on the how we can take advantage of these studies of these basic studies on biological apatite to prepare biomimetic bone substitute materials. And then I will conclude. So to begin, I think you heard a lot during this school on biomineralization because it's the thematic. So usually all this biomineralization involve some elements that are quite similar. We have silicates, calcium carbonates, and today my talk will focus on calcium phosphates. Usually this biomineralization show a very elaborated architecture, an adaptable architecture which is able to grow and repair. Usually these biomineralization are resistant, show mechanical properties and lightness too, and they are formed in a process that will save energy at low temperature with possible renewal, so it's quite really interesting to study in this way. So calcium phosphate, this is what I will talk about, are found in normal and pathological calcifications, and I will focus on apatite, which is encountered in bone and teeth, which is hard tissue in vertebrates, but it's also found in pathological calcification, for example, in the crystal deposition associated with arthritis, or for example in renal calcification. And I will talk about a little bit on other calcium phosphate, octacalcium phosphate, and also amorphous calcium phosphate, sorry. How these biominerals are formed? So usually it needs supersaturated conditions to form. There are usually they nucleate and grow in controlled conditions, and always there is initially an organic matrix, which is substituted in the case of bone formation, which is degraded in the case of dental enamel, which is hypermineralized apatite bones, which is also spread in the case of nacre. If we have a look on the evolution and the function of the involvement of calcium phosphate in living organisms. So at the very beginning there were calcium and phosphate intracellularly. Then it can act as a mineral ions reservoir extracellularly. Then we have other, I will do some gap until, for example, architecture and structuration of the body with fixation and organization of the soft tissue and organs, then the mobility, then the defense, the nutrition with the teeth, for example. So all along the evolution, we preserve the anterior functions of minerals, but also there was adaptation. And I will just briefly show you some adaptive response that we can see. For example, here in bone and tooth, if we compare bone and tooth enamel, they have different architecture, and the first adaptative response lies on the mineral content, with bone involving from 50 to 85% of mineral, depending on the type of bone. And in the case of tooth enamel, we have hypermineralized tissue, which is very close to 100%. The second adaptative response is related to the characteristic of the mineral crystals. In the case of bone, we have nanocrystals, platelets shape, and a high specific surface area. And I will talk later on the role of these characteristics. Whereas in the case of tooth enamel, we have large crystals, needle-like shape with low specific surface area to resist to, for example, acidic attack in the mouth. The third adaptative response is related to the mineral composition. Here you have the well-known stoichiometric hydroxyapatite. And in the case which is never encountered in living organism this way, stoichiometric, and the composition of bone and dental enamel have been proposed. And you can see that it can be related to the stoichiometric hydroxyapatite with some substitution of PU4 with HPU4 and carbonate. And to compensate it for the charge in the mineral, we have an introduction of calcium deficiency vacancy and also hydroxide vacancy. And you can see, if you compare the bone and the dental enamel apatite composition, you can see that bone mineral is more lacunar. There is more vacancy, 1.7 compared to 0.6 here and here also, and soluble than tooth enamel. And so we have an adaptable composition in relation to the tissue function. But for example, for another mineralization based on calcium carbonate, we cannot have such adaptation of the composition for calcium carbonate. So I will talk on bone tissue, especially on bone minerals. So you know that bone tissue is, can be considered as a composite with a great part of mineral, which is not very well known and is more recently studied. So okay, and whereas the organic matrix, almost 22%, is well known and well studied too for a long time. Okay, and among the organics, it is mainly composed of collagen. The main protein is collagen. So I will focus on biological apatite, the bone mineral in bone, especially on the composition, the structure, the formation, and the properties. So if we look at the bone, it shows a very elaborated architecture. I think you probably heard about during this week about it. So if we look more deeply at the molecular level, we have here the collagen fibers with the collagen fibrils, and it has been studied a lot, showing that the mineralization begins in this empty space here. And if we look at the bone mineral crystals, here you have a 4-year-old bovine bone mineral, which is so by TEM, and you can see that it's very thin, irregular platelets. And also, again, here I put the composition of this kind of this apatite, biological apatite. So some questions are still related to the bone mineral, especially on fast composition. I will talk about later. In the presence of hydroxide in bone apatite also, and also the possible presence of precursor phase of apatites which are formed in vivo. So here I talked already on bone mineral composition and dental enamel. Here it's a more general apatite-based biomineralization, where you can see that we can substitute part of the PU4 by HPU4 and carbonate, and also the hydroxide can be substituted by fluoride or carbonate also. So there is really, we can talk about apatite flexibility in terms of composition, and this is what allow the adaptation of the biological function of the tissue. If we look at the structural characteristics, so in apatite, it's a ionic compound. So the cohesiveness of the crystals of the apatite is mainly due to electrostatic interactions. Also, the presence of tunnels inside the structure allows some anions to be incorporated or to disappear from the structure. There are also numerous substitutions which are possible, and also a very large domain of non-stoichiometry. So all this characteristic also is responsible for this possibility to adapt the structure. So the non-stoichiometry consequences show that we have less cohesiveness of the crystal, so higher solubility, more reactivity, thermal also instability, but in the body thermal is not, the variation is not important, and so the biological adaptability. So now I will focus on the question on the hydroxide content in bone apatite. So there are many studies for a long time, and so here there are only some of them that are reported, and you can see that some studies show that there is no presence of OH in bone mineral, whereas some other studies show that we have almost 50% of hydroxide in bone compared to stoichiometric apatites. Here 20%. So there are many studies showing many controversy on the OH content in bone mineral, in bone apatite. So here just I show one of these studies, which are based on Raman spectra study. Okay, so you can see here the study of the spectra of different kind of bones of different origin here, and we can see that here this is the position of the band related to OH content, and here also, and you can see that there is a very faint OH band in all cases. In most of these samples, and if we have a quantitative evaluation, we have here, we can see that it's between 0 and 5% of OH compared to the OH content in stoichiometric apatites. So, well, here, yes, so we have mostly, in most cases, very faint OH band. The discrepancy that we can see in several studies is probably due to the evolution of bone substance with age and with maturation. Okay, so we can suggest it that probably bone can contain some hydroxyapatite clusters, but probably in minute amounts. So this is one of our suggestions. Here, if we have a look to the X-ray diffraction pattern of different bone at different age. So here it's chicken bone, but embryonic, it's 17 days. Then here 5 weeks post-age. And here a 2-year-old chicken. Okay, and here the last one is the synthetic stoichiometric apatite, the diagram of synthetic hydroxyapatite. So you can see that we have an evolution of the crystallinity of the apatite during aging. Okay, so we have in all cases the apatite structure, but variable crystallinity. Also, if we observe the morphology of the crystals, which are platelet-like morphology, elongated along the C-axis of the structure, it is far from the usual needle-like shape we currently we can see usually for apatite crystal. So this observation also raised the question of, is there possible precursor phase of biological apatites? Among the possible precursor phase, there are amorphous calcium phosphate, octacalcium phosphate, and dicalcium phosphate dihydrate. And I will have just one slide for each of the, for amorphous I will have more than one slide, but just to give you some information about each of these phases. So the problem to study and to identify amorphous calcium phosphate is important because we have low amount of biological materials, biological samples. Also, the sample preparation can, there are risks of phase alteration, modification during sample preparation. And so there is a risk of evolution or crystallization of amorphous calcium phosphate during sample preparation. And also we have the limit of the analytical techniques because this is not a structure material, structure phase. So the question is also, can we talk about amorphous phase or amorphous domains inside in apatite structure, for example? So just a brief history on the studies of 50 years of studies also and of controversies of the presence of precursor of amorphous calcium phosphate precursor of apatites, and is still today under debate. So there is a growing interest on this theory of the amorphous mineral precursor phase, which is also a growing interest for amorphous calcium phosphate, but also for other amorphous phase of biominerals. But if we look at all these studies, there is still a lack of irrefutable proofs for the presence of this amorphous phase, precursor phase, in mineralized tissue or in newly formed calcifications. So just one of the illustration is an old study is the cluster which have been proposed by Posner, showing that there is a lack of long-range structural order, and here we can see the relation of this cluster, of this amorphous calcium phosphate cluster related to the apatite structure, its relationship with the apatite structure. And so Posner suggested that there is an age dependency of the amorphous and crystalline mineral fraction in bones, saying that there is an amorphous fraction and also a crystalline fraction in bone. But this study was later refuted, and there is some evolution of this conception. So another illustration is the work that have been done to show if OCP, the other calcium phosphate, that have been proposed as a precursor of apatite in vivo. So OCP, you have here the chemical formula. It is a hydrated calcium phosphate, like decalcium, like bruchite also. So there are some characteristics that are in favor of proposing this phase as a precursor. He has a low calcium and phosphorus ratio, lower than stoichiometric apatite, so more closer to biological apatite. It has elongated platelet-shaped crystals, which are closer to what we saw for biological apatite. There are also some analogy of the characteristic, especially of the spectroscopic characteristic. But there is also some features that are against this theory of the OCP precursor. There are also, even if there is some analogy, there is also several anomalies in the FTRS spectrum of OCP compared to biological apatite. And also one important thing is that we don't have the presence of carbonate inside OCP, whereas we know that carbonate is present even at the early stages of biomineralization. So, well, this is still under debate, but there is some discussion to have. Here, just one or two comments on the possibility to have DCPD as a precursor phase of apatite in vivo. This hypothesis has little support today. A few years ago, there are some studies on this, but now it's still less reliable studies. So, okay, DCPD is one of the calcium phosphate that are formed mostly in acidic conditions, so lower than the physiological pHs. However, we know that when apatite form, the formation of apatite will induce a decrease of the pH. So why not, during apatite formation, consider that DCPD can form also, because we have a decrease of the pH, so we can reach some conditions that are okay for the formation of this phase. So this is my last slide on this question of the precursor phase of apatite. And here, so to continue the story, the problem is that, as I told you, apatite have been, bone mineral have been studied very later than the organic part of bone. So there is really a problem of the characterization of these materials, these biological materials, because there is biological variability depending on the origin of bone, the species, the age, several characteristics. There is also, this is a heterogeneous materials, because we know that during aging there is remodeling of bone all along our life. So we have a photography of the bone at one time, but we have more or less newly formed bone in the same materials. Also, we have an intimate association of this bone mineral with the organic matrix, which is complicated to study this. And also, one of the main problems is that this apatite is not well crystallized. So we lack of analytical method to study this material. And for example, in the 90s, several groups have worked on this bone mineral. And especially they show by FTIR spectroscopy with a fine analysis of for example here, of the new 4PU4 band domain. Fine analysis by decomposition of this domain. They have showed that we can, there is a line, FTIR line or band, subband, that are specific to special environments of phosphate and also of carbonates, which are not really the same because this is not at the same vibration energy, wave number, that are different from that in stoichiometric apatite, in apatite structure. So they call this non-apatitic HPU4, PU4 and carbonate species. And they show that these species are evolving during bone mineral maturation with age. For example, we have a decrease of the HPU4 content, an increase of the carbonate content, but with age we have a decrease of this non-apatitic environment present in bone. Whereas we have also a slight increase of nanocrystal size and also an increase of crystalline order with age. So we have several characteristics due to the evolution of bone with age, and the question is what is the significance and the consequences of this evolution on biological apatite properties. So to try to go further and to try to better understand what are the properties of this biological apatite, we develop an approach based on synthetic apatites. Why it is interesting to work with also synthetic apatite crystals. The first thing is that you can have apatite in larger amount, so you have more materials to do, for example, structural studies, to do nucleation and crystal growth study, to do dissolution property study, and to study the absorption and the role of molecules or ions on the formation of this synthetic apatites. And so the final objective is to participate in the understanding of normal and pathological mineralization. But also I will show you at the end of my talk that this study on synthetic apatite can also aid in the development of bioactive bone substitute materials. So the second part of my talk will focus on the synthesis, the characterization and the properties of nanocrystalline apatite, synthetic nanocrystalline apatite, analogous to bone mineral. But also I will compare the results obtained with this kind of apatite compared to what we can see with biological apatite. So just a brief, I have two slides on just to compare what we have when we do chemical precipitation, synthesis of apatite, versus the biological formation. So in chemical synthesis, usually we have a fast precipitation with concentrated solution, quite clean. Well, we can control the purity of the solution of the preparation, and we usually have homogeneous samples, and we can mostly control the formation and doing specific studies. And mostly we have precipitation through homogeneous nucleation. Whereas in biological formation, biomineralization, we usually have mostly slow formation. The solution are more dilute than in the case of synthetic chemical synthesis. We have also the presence of many organic components that can act during this formation, and also the formation is mainly based on heterogeneous nucleation. Especially, I talked to you that the first crystal, it is now well accepted that the first crystals are formed within the holes between the collagen fibrils. Okay, also what are the parameters that are involved in chemical synthesis versus biological formation? So in chemical synthesis, we have several parameters. The main are the pH and the temperature, whereas in biological formation, well, pH perhaps we have, also the concentration of ions locally. This concentration can be modified. the presence of nucleating substance and adsorbed species. So here a slide presenting how we can prepare synthetic nanocrystalline apatite analogous to bone mineral. It's quite easy, an easy way to prepare in solution by precipitation from a calcium carbonate solution and hydrogenophosphate solution. This precipitation is at ambient temperature and at physiological pH. And here you can see a general formula of the apatite that we can prepare. This is a general formula because depending on we can add also carbonate in the solution to prepare a carbonated apatite, and we can also eventually change the pH to prepare more or less hydroxylated apatite. And you can see here, after 1 day of maturation of this crystal, after precipitation, we have TEM here micrograph showing that we have also this irregular shape platelet crystals. So based on this synthetic nanocrystalline apatite, we perform some studies to better know the properties of maturation, ion exchange, and also protein absorption of these synthetic apatites. So the aim of this study is to better know the origin of the surface reactivity of biological but also nanocrystalline apatites, and to develop tools for the quantitative evaluation of this reactivity. So we use some spectroscopic techniques, but also some diffraction methods to have more or less information on long-range order, and also a study on the chemical reactivity with some exchange experiments and synthesis and maturation experiments too. So, for example, here we compare the composition, especially the calcium and phosphorus ratio, and for carbonated apatite, we compare here the calcium on phosphate plus carbonate ratio. For synthetic carbonated apatite maturated at different period, after different period of time. And here we can see the same analysis on the calcium, the same ratio for chicken bone at different age. Okay, 7 days, embryonic 7 days, 16 days, excuse me, 4 weeks until 70 weeks. And you can see that you have quite, different calcium and phosphorus ratio, whereas if you look at the calcium and phosphorus plus carbonate ratio, we are more in the same range of chemical composition. If we look at the characterization by FTIR spectroscopy, so here you have the example of spectra of bone sample of different origin here in the new 4Pu4 domain. And here we have synthetic nanocrystalline apatite, I forget to add apatite, with OH content between 5 and 50%. Compared to stoichiometric hydroxyapatite. So the line that are interesting is here in the left side of this domain. So you can see that when we increase in synthetic apatite the OH content, we have an increase of the intensity of this subband, whereas here in the various bone sample we no distinct OH bands can be found in bone. Well, just here, just to see, this is the new 4Pu4 domain and the example of decomposition of, this is the cow bone, so the one who will be this one that we decompose here. And you know, the band characteristic of OH is here, but it's here, but you cannot see because it's very faint, okay, after decomposition. Okay, here some results related to the characterization, the structure characterization. So here this is a reference stoichiometric hydroxyapatite pattern. Here nanocrystalline apatite after 1 month of maturation, and here it's a rat bone, months old. So to have an evaluation of the crystal size of these crystals, we particularly look at this line 002 and 310 to have an idea of the apparent size of the crystallite. With this band we have an information on the length of the platelets, and here with the 310 we have an evaluation of the width and thickness of the platelets crystals. So here you have the value for different bone, animal and human, and the value for synthetic apatite after 3 months of maturation. So you can see, so 3 months of maturation, it's one of the biggest nanocrystals that we prepare in our lab, and you see that it's higher in length than the other example. And here we have an evaluation of the crystal size, the apparent crystal size for synthetic nanocrystalline apatite, not carbonated apatite, and you have, so here the length, oh sorry, it's 002, this is not 200, and in here the 310 line, and you can see that at 3 months this is one of the larger crystals that we can obtain. So we have the width and thickness, it's quite almost the same with maturation, whereas if you look at the length, you can see that we have slightly an increase of the length of the crystals with aging. So, okay, this is another important component of biological apatite. It's HPU4. HPU4, it's an important marker of nanocrystalline apatite maturation. And it's difficult to evaluate, to have a quantitative analysis of this component. And so there is an analytical technique proposed, which is an old, but it's okay, it's a good one also, but it's really difficult to do this analysis. And so we propose, a few years ago, we proposed a method based on the evaluation of the band intensity of the non-apatitic and apatitic HPU4 band on the FTIR spectra, and we can see that we have quite a good correlation between the evaluation by FTIR spectroscopy and the evaluation with chemical analysis. So, and we then choose the FTIR spectroscopy method because it's more fast, it's faster to have the results, and it's quite straightforward. So if we apply now this method to evaluate the HPU4 content in synthetic apatite with different maturation, here from 0 to 1 month, you can see here that the HPU4 content is decreasing with aging, and if we compare with the evolution of this HPU4 content in chicken bone from embryonic to 3 years, you can see also that you have a small decrease of this HPU4 content with maturation in the case of synthetic, and with aging in the case of biological apatite. We are interested also in another property of nanocrystalline apatite, which is the ionic exchange property. So this results are on synthetic nanocrystalline apatite. So here we studied the cation exchange properties of apatite. So AC, it's carbonated apatite, And what we do is we studied the exchange property of this apatite with maturation time. And especially we studied the exchange of strontium ions with calcium ions. So firstly, we put the apatite in a strontium solution, and you can see here that the ability, so here this is the ratio strontium on strontium plus calcium, which give you an idea of the ability of this apatite to exchange strontium with calcium. So you can see that the amount of strontium that can be incorporated in the apatite is decreasing with maturation. And then if we perform the reverse exchange, we put this apatite that have been already exchanged with strontium, we put it in calcium solution. And you can see here that we evaluate the amount of strontium. You can see that mostly all the strontium have been exchanged, whatever the maturation age. Mostly all the strontium have been reversibly exchanged. But you have a small amount of strontium that still remain irreversibly fixed, incorporated in the apatite. This exchange with strontium and then with calcium is fast, less than 10 minutes. And it's reversible. We can see that it's reversible. We performed quite the same experiment with anionic exchange between carbonate and hydrogenophosphate. And we use here FTIR spectroscopy to determine this exchange ability, this anionic exchange ability. So here you have the spectra of the carbonate apatite mature with 1 day of maturation. This apatite, we put it in a solution with carbonate 13. Carbonate 13 to see the shift of the bond. And you can see here that you can see the carbonate 13 that have been exchanged with the apatite. Okay, and then if this apatite, you put this apatite in a HPU4 solution, you can see that these bonds are decreasing a lot, showing that most of the carbonate 13 that have been firstly exchanged is reversibly exchanged with the HPU4 in the case of reversible exchanges. So this is a very interesting ability of this nanocrystalline apatite that are involved in fast and reversible exchange properties. And if we compare here, so you have here the relative percent of exchange ions with maturation time of nanocrystalline apatite. So here you have the curve for strontium and calcium, and here the curve carbonate HPU4 exchange. And just to see that here we put the result found when we perform exchange on calf bone. The bone is ground. So it's quite, we were very surprised that this value is quite high also for biological bone, so for biological apatite. So there is also a high capacity of ionic exchange for biological apatite. Here I have a slide, 1 or 2 slides on the role of water, which you will see appear really important in this kind of apatite. Here you have the spectra, the FTIR spectra of an apatite, nanocrystalline apatite, which is here as a gel, so with high amount of water, and we leave this apatite drying on the spectrometer. And so you can see that we have, with drying, you have a loss of the fine features of the spectra of the band, probably related to a disordered ionic layer due to the loss of water. And a short range order alteration upon drying, probably. And here, after drying, we have a spectra which presents some analogy with amorphous calcium phosphate, but we for sure it's different. Some analogy, but it's different. Here, this is a 31 phosphorus NMR study to show nanocrystalline apatite in wet state, and here the same analysis on a lyophilized apatite, so dried apatite. And here also you can see that the fine feature of this band is also lost. So these fine structural details are disappeared upon drying. So probably this experiment show that if probably the loss of water alter the non-apathetic environment. So it seems that there is a very fragile surface hydrated layer structure at the surface of the nanocrystals of apatite. And here also on the spectra and the NMR spectra we have some analogy, but with the proposed precursor of apatite, OCP and DCPD, but this is different. Finally, on the studies of properties of nanocrystalline apatite, here I show the example of bovine serum albumin adsorption on nanocrystalline apatite as a function of maturation time of apatite. So you can see that the maximum coverage of BSA on nanocrystalline apatite is decreasing with maturation time, whereas you have the affinity constant of the adsorption of BSA on nanocrystalline apatite that increased with maturation time. So it seems that the adsorption properties vary according to the surface layer characteristic of the apatite. And these results can suggest that there is a possible control of bone mineral maturation state and property of this surface layer. So depending on the extent of the surface layer upon aging, you can have a control of these properties. So all these results and studies allow us to propose a model for the apatite nanocrystals. So this is a model we proposed. This is the schematic representation of nanocrystals. So you can see here at the core of the crystal we have an apathetic structure. So we have calcium, phosphate, carbonate in well-defined environment. Well known also, apathetic in apathetic domain. And on the surface we propose that there is a structure hydrated layer, and the extent of this surface hydrated layer at the surface of these crystals depends on the age of the maturation stage of the apatite. So if we look here, this is like a cross section of the crystal here. So you have here the apathetic domain. The surface layer including several divalent ions, and these divalent ions can be easily exchanged with the environment, the solution, with proteins or HPU4 carbonate or calcium. And so this conception is different from the first conception that have been a long time ago proposed, that there were an amorphous phase and then a crystalline phase in bones. So here we propose that is not really two phases, but there is domains in these crystals. So how this model can explain what we saw biologically. So with time, so here you have a representation of a nanocrystal So he's spherical, but it's not. It's just a schematic representation. So here you have the apatite domain and the extent of the hydrated layer here. And with time, you have the apatitic domain that are growing at the expense of the hydrated layer, and so. These domains evolve progressively towards a stable apatitic lattice, and which means a more crystalline phase. And the H2O4 content, which are mainly related to this layer, is decreasing also. And also we have an increase of crystal size and perfection related to the extent of this apatitic domain here. So a final question that I would like to talk about with you is, we propose this model involving a surface hydrate layer, the surface of crystals of apatite. But what is the reason of such hydrated layer in vivo? Is there some interest in suggesting this kind of conception of crystals? So an example, just to talk a little bit about the precursor we talked about at the beginning of this presentation. So apatite is the most stable structure at physiological pH. Okay. So, however, apatite, the crystal growth of apatite is very low. It's a very slow process. So why not thinking of possibly precursor phase of this apatite? And if we look at the interfacial tension of OCP or DCPD, which are precursor phase that have been proposed of apatite, we can see that they have a very much lower interfacial energy than the one of hydroxyapatite or fluoroapatite that are closer to bone enamel apatite, to tooth enamel, apatite. So it seems that the hydrated calcium phosphates have a reduced interfacial energy to compare to stoichiometric hydroxyapatite, which does not have any hydrated layer at its surface. So it seems that this hydrated layer could stabilize the nanocrystal of apatite. So remember at the beginning of my talk, I talked about the first adaptative response based on the mineral content. The second adaptative response was related to the mineral crystals, the shape and the size of the crystals. The third adaptative response was related to the composition of apatite, and here we propose the fourth adaptative response based on this model we propose and based on the surface characteristics of the crystals of apatite. So this model of hydrated surface layer can explain the surface reactivity of the apatite crystals, especially the ion exchange capacity, the maturation ability of bone, and also the necessity of the bone remodeling if we want to preserve the reactivity of bone, especially its exchangeability. And also the involvement of this surface hydrate layer with the interaction between apatite and also the organic part of the bone matrix. And this interaction could be involved during bone mineral formation, also and bone mineral growth, nucleation and growth. So to finish my talk here on what are the consequences also of the presence of this hydrated layer to go to go further especially to prepare bond substitute materials. So here you can see the schematic representation of two nanocrystals, so the apatitic domain and the surface hydrated layer, and also so we can, oh sorry, there is some change here, sorry. You can see two crystals that are a fusion of two crystals, and this through this hydrated layer. So we can think that upon drying we can have a strong interaction of the nanocrystals by drying, so elimination of water, and this concept can be we can take advantage of this possibility to prepare low temperature ceramics, coatings or composites, for example. And in aqueous media we can have interaction also between the crystals, and with exchange here of several ions. And this property of exchange of ions can be involved also in the setting reaction of calcium phosphate cements that are also used as biomaterial. So yes, this is just a brief review of the model we proposed. So the four characteristics of the biomimetic apatite is related to their structure, their composition. So this is non-stoichiometric apatite that can include HPU4 or carbonate ions. This is a nanocrystal, so the size is nano. The shape is unusual with a platelet-like shape. The surface is really reactive. So the challenge for a material scientist is how to keep these characteristics during material processing. Because if we want to have a bioactive bond substitute materials, it's important to keep this characteristic of the surface characteristics, but also the shape and the nano size of this apatite during processing. So there is just a few examples here. Example of the consolidation of biomimetic apatite by spark plasma sintering. So sintering, usually the commercial hydroxyapatite ceramics that are used as bond substitute are prepared at very high temperature, mainly at more 1100 degrees Celsius, so it's very high temperature. So at this temperature you have no more hydrated layer, no more reactivity. So if we want to keep this surface hydrated layer, we propose this processing, which can be, we can have a sintering, a consolidation. So we have, at the beginning we have a powder, nanocrystal, and then we would like to have a bulk ceramic. So we saw that we can have a sintering process using sparse plasma sintering at only 150 degrees Celsius. So it's really very interesting because comparing 150 degrees Celsius compared to 1100, it's very different. So here you have a photography of the ceramics, of the bulk ceramics we can prepare. So we use a pressure, sorry, the pressure is 100 megapascal, and this temperature. And you can see that this is the nanocrystalline apatite powder before sintering, and you have here the ground ceramics. So you can see that after sintering you keep the nanocrystallinity, the non-stoichiometry, so you preserve the nanostructuration, and also what is important, we preserve mostly the hydrated layer of the apatite, so we can have a more bioactive ceramics. Another example here, it's based on a coating, a nanocrystalline coating we work on, and we perform this coating on the well-known granules, biphasic granules. So this is a commercial products, granules, porous granules, made of hydroxyapatite, stoichiometric hydroxyapatite, and TCP. This is a classical ceramic, porous ceramics. And the idea was to try to activate these ceramics to increase the osteointegration and the bioactivity of these ceramics. So we proposed to perform a coating. So this is the commercial ceramics porous here. So we proposed to cover all the pores with a coating of nanocrystalline apatite. So here you have in yellow the coating. And then we also propose, due to the ability of this nanocrystalline apatite to absorb and release proteins, or we propose to absorb BMP2, which is a growth factor, well known to have an impact on the osteogenesis. So, okay, so we have the commercial, we have three kinds of materials that have been tested: the commercial porous ceramics, the coated porous ceramics, and the coated and functionalized with BNP ceramics. Okay, so you have a SEM micrograph of the raw. So this is the commercial granule here, the raw surface, and here with the coating you have a fine coating. Nanostructure, a fine coating. So here you have the ability of BMP2, the growth factor, to absorb on the granules. So in here the raw granules without the coating, so you see that there is a lower amount of adsorbed BMP compared to the coated granule, sorry. The granules coated with nanocrystalline apatite. So you can see that the coating really enhance the ability of the ceramics to absorb this growth factor. So we implanted these materials, the raw ceramics, the coated ceramics, and the coated functionalized ceramics in sheep during 3 months. And you have here the histology cross section of sample of the without BMP, without the growth factor. So here you have the raw granules, and here the coated granules. Okay, without BMP2, and so you can distinguish. So in blue, this is the neoform bone in blue. Okay, so you can see that on the raw granules you have some layer of neoform bone tissue, but it's quite low. Whereas in the case of the coated granules with nanocrystalline apatite, you can clearly see a quite more important neoform bone here in blue, and you can see that the neoformation of bone is really at the surface of the pore of the granules. Okay, and if we have a quantitative evaluation of this bone neoformation, so here we compare the raw granules, the commercial granules, here the coated granules, and here the coated with BNP and raw with only BNP, it means without the coating. Okay, so what we can see, previously we think that this one would be the best, but what we saw is that with only the coating we have quite the same results that with coating with BNP, and it's much more easier to prepare and commercialize ceramics without BNP, because it's less expensive. It's also better for our health social organism also. So with only the coating of the nanocrystalline apatite, we have greatly improved the formation of bone. And this work have been there is a technology transfer, and is now commercialized by Technimed company, and the product is Seraform Revolution. Just to finish, an example also on this work on nanocrystalline apatite, and especially on the study on the interaction of biphosphonates with apatites. This is an in vitro study. So biphosphonates is an anti-resorption agent. We have a double action, a physico-chemical action and a biological action. They are mainly used to for the treatment of various bone diseases. And the work which was performed in our lab here the idea was to, firstly, to understand what are the interaction between the biphosphonate and nanocrystalline apatite, to better know the action, the physico-chemical action of these molecules in contact with bone and bone apatite, and also to develop a biomimetic drug delivery system for osteoporosis treatment. So what we demonstrate is that the interaction of biphosphonate with apatite is based on like an ionic exchange between the phosphate of apatite and the biphosphonate in solution. And there is, we found that there is between 1 and 2 exchange molecules depending on the type of biphosphonate, because there is several types of biphosphonate depending on the on one of the groupments on the POP bond. If we look at the release kinetics of adsorb biphosphonate on nanocrystalline apatite. So here we have a very fresh precipitated apatite with no carbonate and no maturation, which it's close to a newly formed bone. And here we have a 1 month maturation apatite and with carbonate, which characterizes an older bone. Okay, so in all cases, you can see that the release of biphosphonate is quite slow, because after 8 hours we have less than 5% of biphosphonate that are released. Okay, so there is a low and a slow release of this biphosphonate. And we also perform studies in contact with human bone marrow stroma cells and also on osteoclasts. So osteoblast on osteoblast or pre-osteoblast cells to see the proliferation, the adhesion, the proliferation and the differentiation of these cells in contact with nanocrystalline apatite and nanocrystalline apatite with bisphosphonates. And so we can see that after 7 days of test, we have the cells that are spreading, better spread of the cells when we have bisphosphonates. And here a test with osteoclasts, so the cells that are in charge of the resorption of bone. And we have a look to the resorption lacunae after 3 days of culture, and you can see that when on apatite you have here several lacunae, resorption lacunae, but when we have adsorbed biphosphonate on apatite, the number of lacunae really decrease a lot. So to conclude my talk, okay, sorry. So I think you see that bone mineral is a very reactive, complex compound and structure. The evolution of bone apatite with age we show that correspond to a physical-chemical maturation process. We show also that nanocrystalline apatite shows specific surface structure in aqueous media when it is hydrated. We show that this hydrated layer is unstable. It can disappear upon drying. This structure hydrated layer offer ion exchange and protein adsorption capabilities of for these crystals. And this surface reactivity can thus be utilized by living organisms And also the surface reactivity can be controlled to prepare new biomaterials at low temperature. And this talk is to show you also that the progresses in the understanding of biomineralization on the mineral, bone mineral structure, composition, properties is mainly related to the progress in characterization and also on the progress based on the synthetic nanocrystalline apatite, on the study on synthetic also nanocrystalline apatite. So I would like to thank you for your attention, and if you have any question.